My dear students, let me welcome you all to a new edition of physics. In this edition, we'll learn how to convert the moving coil galvanometer into a device that directly measures electrical resistance. We'll learn about the ohmmeter, how to calibrate the ohmmeter, why the scale of the ohmmeter is not a uniform one, why it is reversed to that of the milliammeter. So let's get started. Ohmmeter. Okay, what about the ohmmeter? Is a device which directly measures the electric resistance. Talking about the ohmmeter. It is a device used for measuring, yes, the electric resistance directly. What about the structure of the ohmmeter? As a matter of fact, it consists of a galvanometer, okay, whose resistance is 250 ohm. Its full scale deflection 400 microampere. And we've got a variable resistance, okay, ranging from 0 up to 6,565 ohm, and a cell 1.5 volt. And standard resistance, what about it? It is 3,000 ohm standard resistance. Okay, so it consists of a microammeter, a galvanometer, having resistance 250, and gives the full scale deflection for a current of 400 microampere. Also, we have 1.5 volt cell, a standard fixed resistor 3000 ohm, a variable resistance ranging from 0 up to 6565. Okay. First of all, what is the function of the fixed resistor? Without the fixed resistor, without RS, the current flowing in the galvanometer would be too excessive. Okay, without RS, the current would be, yes, so high. The current would be too excessive. It would damage the galvanometer. It would simply heat its coil and burn it out. Okay. And what about the function of the variable resistance? Each time the ohmmeter is used, it is first short-circuited. So each time you want to use the ohmmeter, it should be short-circuited. It is short-circuited. What does it mean? The variable resistance is adjusted to zero the device, to set the device at 0, to give the full scale deflection of the current, which is 0 deflection of the ohmmeter. This was about the function of the variable resistance. And what about the current passing when we obtain the full scale deflection? Ig equals VB. VB is the EMF of the cell. Rg is the value of the resistance of the galvanometer. Rs is the value of the standard fixed resistor. Rv is the chosen value of the variable resistor. Small r is the internal resistance of the cell. Okay. And now, how to calibrate the ohmmeter? What does it mean? How to build up a scale for resistance? We've already got a scale for current, the scale of the galvanometer. Okay, but we want to build up a scale for resistance. We call this calibration of the device, calibration of the ohmmeter. Okay, so the device is calibrated by inserting known resistance between the test terminals. Okay. For example, a resistance of 1 ohm. So what happens? The pointer moves backwards. Each time a known resistance is inserted between the test terminals, the pointer moves backwards to a position where the value of the resistance is written. Okay, we repeat with another resistance, for example, 2 ohm resistor. Yes, it returns back once again, and the value of the resistance is written, and so on. In this way, the scale of the device is built up. Okay, now measuring an unknown resistance. The unknown resistance, denoted by R, is inserted between the test terminal, and the pointer directly reads its value. The unknown resistance is inserted between the test terminals, and the pointer directly reads its value. When measuring an external resistance, the current, of course, will not be Ig. It will be less than Ig, and it is equal to VB over Rg plus Rs plus Rv plus internal resistance plus R required to be measured. VB is the EMF of the cell, Rg is the resistance of the galvanometer, Rs is the fixed one, the standard resistance, and Rv is the chosen value of the variable resistance. Internal resistance of the cell is denoted by small r. Resistance required to be measured is capital R. Okay. And now we've got 2 important give reasons. First of all, give reason. The ohmmeter scale is reversed to the microammeter scale. The ohmmeter scale is reversed to the galvanometer scale. Why? Okay, it's all easy because the current intensity flowing in the device is inversely, the current is inversely proportional to the total resistance. So when the resistance increases, the current decreases. And this explains why the scale of the device, the scale of the ohmmeter, is reversed to that of the galvanometer. Another important give reason, the ohmmeter scale is not an evenly divided scale. It's not linear. It's not uniform. The ohmmeter scale is not an evenly divided scale because, yes, the current is inversely proportional to the total resistance. It is inversely proportional to the total resistance. It's not inversely proportional to the resistance required to be measured. Okay, that's why the scale is not uniform, because the current is inversely proportional to the total resistance, not with the resistance required to be measured. And now let's solve some problems. A milliammeter of resistance 5 ohm. Okay, what about this given value? What is this 5 ohm? It is Rg. A milliammeter reads its full scale deflection for a current of, yes, 15 milliampere. 15 milliampere is Ig. Milli is converted into ampere. It is multiplied by 10 power negative 3. A milliammeter of resistance 5 ohm reads full scale deflection for a current of 15 milliampere. It is desired to convert it into ohmmeter using a cell 1.5 volt of internal resistance 1 ohm. So the cell, yes, has an EMF of 1.5. Its internal resistance is 1 ohm. Okay. Also, we want you to calculate the external resistance, which when connected to the ohmmeter, okay, the pointer of the milliammeter reads 10 milliampere. Okay, we'll take it one by one. Resistance of the galvanometer mentioned in the problem, yes, it is 5 ohms. Full scale deflection, 15 times 10 power negative 3, 15 milliampere. And it is converted into ampere, it is multiplied by 10 power negative 3. Internal resistance of the cell, 1 ohm, and the EMF of the cell is equal to 1.5. So maximum current, okay, equals VB over RG is the resistance of the galvanometer plus RS and RV. RS is the standard fixed resistor, RV is the chosen value of the variable resistor. We call both of them R conversion, plus R internal. Okay, so I maximum equals VB over RG plus R conversion plus small r. R conversion, as I said, as I mentioned, it is the sum of RS plus RV. RS is standard resistor, RV is the variable one. So 15 times 10 power negative 3 equals 1.5 over 5 plus 1 plus R conversion. And this way, it's all easy to obtain the value of the, yes, R conversion, the resistance required to convert the galvanometer or the milliammeter into an ohmmeter. We need a resistance of, yes, 94 ohm. Now, we'll measure an external resistance, and the current drops to be 10 to the power 10 times 10 to the power of negative 3. Okay, once again, we'll apply Ohm's law of closed circuit. It is equal to 1.5 over resistance of the galvanometer 5 plus R internal 1 plus R conversion plus the external, yes, resistance measured. In this way, we managed to obtain it. It is 50 ohms. Another type of questions. What happens when? In front of you, we've got two wires carrying currents in the same direction. Okay? As a matter of fact, the distance between the two wires is denoted by D. Each one of them carry current I. It means they carry the same current intensity in the same direction, okay? So fields produced by the currents outside the wires have the same direction. Between the two wires, they're opposite directions. So what happens? Attraction occurs between these two wires. And what about the question? What happens when the current in each wire is doubled? Distance between the two wires is made 4 times greater, is quadrupled, while the direction of the current in just one of them, in wire A, is reversed. So current in each wire is doubled, distance is made 4 times greater, and direction of the current in one of them is reversed. And we want you to tell what would happen. Okay. With respect to the magnitude and kind of the force per unit length acting on each wire. Okay. Since the force is determined from the expression F is equal to 2 times 10 to the power of negative 7, I1, I2, L over D. This is the force that determines the size, or this is the expression that determines the size of the force. 2 times 10 to the power of negative 7, I1, I2, L over D. So it is equal to 2 times 10 power negative 7, I squared, L over D. I squared because they carry the same current intensity. So we'll, yes, modify this expression. We can say F1 over F2 is equal to I1 over I2 all squared, D2 over D1. Current is doubled, so I2 equals 2I1. distance is made 4 times greater, so d2 equals 4 d1. Okay, so we can say f1 over f2 equals I1 over I2 all squared. I2 equals 2I1. Okay, d2 over d1, d2 equals 4 d1, and it will be 4 over 4, it is 1. It means the force remains unchanged. Size of the force is unchanged. Okay, but as I said, magnitude of the force remains unchanged, but the force becomes, yes, repulsive one. Kind of the force changes, and instead of being attraction force, it will be repulsion force. Okay. What happens when the shunt in an ammeter is replaced with another of lower resistance? The question, yes, means we've got a shunt, we replace it with another shunt, but the second shunt has a lower resistance. So what happens when the shunt in an ammeter is replaced with another of lower resistance? With respect to the sensitivity of the ammeter and with respect to the maximum current that the ammeter can read, can measure. Replacing the shunt with another one having lower resistor. Okay. Sensitivity of the ammeter decreases. By the way, sensitivity decreases means the device, yes, becomes able to measure higher current intensity. Sensitivity of the ammeter decreases, and the ammeter can read greater currents. In front of you, we've got a question. What about it? We've got, yes, a circuit that consists of a cell, effect that consists of a cell, effect 1. We've got 2 voltmeters, one located across the cell, and it measures terminal voltage. V2 measures the voltage across R2, and the circuit is open. So V1 now is maximum, and it is equal to EMF of the cell. But V2 is now equal to 0. Yes. What happens when the switch in the circuit shown in front of you is closed with respect to the readings on the 2 voltmeters? Okay. As a matter of fact, V1 was maximum. When closing it, it decreases. And what about V2? V2 was 0. But when closing the switch, it, yes, reads a greater value. So V1 decreases, but V2, yes. V1 decreases, but V2 increases. V1 decreases, but V2 increases. Another question in front of you, same circuit, but the circuit is closed. Okay, we've got R2, which is a fixed resistor, and a voltmeter across this resistance to read the voltage across it alone. And V1 reads the terminal voltage, the external voltage. What happens when the value of R1 is increased? What happens when the value of R1 is increased with respect to the readings on the voltmeters? Okay. When increasing R1, V1 will increase, but V2 will be decreased. We'll explain this. V1 increases, but V2 decreases. Why? Increasing the value of the variable resistance increases the total resistance of the circuit. Of course, total resistance of the circuit is the sum of the internal resistance of the cell and R1 and R2. So when R1 is increased, total resistance of the circuit increases. And what about the current passing through the circuit? Of course, it will be decreased. Okay, so increasing the value of the variable resistance increases the total resistance of the circuit, so the current through the battery decreases. When the current decreases, internal voltage decreases. And when internal voltage decreases, external voltage increases. So the current through the battery decreases, which results in a decrease in the internal voltage. So terminal voltage, denoted by V1, increases. And what about V2? V2 is the product of the current and R2. R2 is constant. What happened to the current? The current decreased, so V2 decreases. V2 decreases as it is proportional to the current. Okay. What happens when the switch K2 in the circuit shown in front of you is closed? As a matter of fact, when closing this switch, we are disconnecting R1. Disconnecting a resistance means decreasing the total resistance. So what happens when the switch in the circuit is closed with respect to the reading on the voltmeter and that on the ammeter? Okay, V decreases, but reading of the meter increases. We'll explain this. When closing the switch disconnects, as I said, R1. So total resistance is decreased. So when resistance decreases, current increases. So the current passing through the battery, through the whole circuit increases. Okay, and when the current increases, internal voltage increases, but external voltage decreases. Okay, so internal voltage decreases, but terminal voltage, so internal voltage increases, but terminal voltage decreases. Another type of questions: when does each of the following quantities equal 0? The torque acting on a coil carrying an electric current and placed in a uniform magnetic field. When does the torque? Yes, is 0. This happens in the vertical position. The torque equals 0 in the vertical position, where the plane of the coil is perpendicular to the magnetic field. The torque is determined from the expression T is equal to BIA and cosine theta. So torque is equal to 0 when theta equals 90, because cosine 90 is 0. Okay, when does the magnetic flux at any point along the axis of a current-carrying solenoid, yes, equal 0? It's all easy. It happens when the solenoid is made of a doubly wound wire. So the coil is made of a doubly wound wire, so the field inside it is equal to 0. When does the force of a magnetic field on a current-carrying wire, yes, equal 0? When the wire, of course, is placed parallel to the field. The force is determined from 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 the force is determined from. When does the terminal voltage across a cell, yes, equal 0? When the cell is short-circuited. What does it mean, short-circuited? When the terminals of the cell is, when the terminals are connected, yes, to a wire of 0 resistance, a wire having no resistance, we call this the circuit, or the cell is short-circuited. Then terminal voltage equals 0. Difference between EMF of a cell and its terminal voltage equals 0. Actually, the problem asks for when does the value of the terminal voltage, so the difference between them is 0. This happens when the circuit of the cell is open. That's to say, the resistance across the terminals of the cell is infinite. No current passes through the battery. Then V external is equal to V battery, and no current flows through the circuit. Okay, also there is another possibility at which V external, V terminal is equal to V battery, when the internal resistance of the cell is equal to 0. Another type of questions, what are the conditions necessary for a coil to be a non-inductive coil? Okay, the coil is made of a doubly wound wire. What are the conditions required for the neutral point to lie outside two current carrying straight wires? Okay, so we have two wires, two straight wires that carry currents, and we want to have the neutral point outside the two wires. Okay, what are the conditions? Of course, thank you very much. This happens when the two wires carry currents in opposite directions. So the two wires should carry currents in the opposite directions. What are the conditions required for obtaining a linear scale in the moving coil galvanometer? What does it mean, linear scale? Linear scale means uniform scale, equally spaced, equally divided scale. We want to have, yes, a galvanometer with a linear scale. What are the conditions? First of all, the poles of the magnet should be curved. Poles of the permanent magnet used should be curved. The coil of the galvanometer should be wrapped around a soft iron cylinder. So we need, yes, the presence of a core, soft iron core. The coil should be wrapped around a soft iron core to produce radial magnetic flux. In this way, we'll obtain, yes, a uniform scale. So the coil of the galvanometer should be wrapped around a soft iron cylinder. In this way, the flux lines will be radial and the scale will be uniform. In this way, we've come to the end of this edition. Until we meet again, my best wishes to you all. Thank you.